So we have talked about Spark batch processing, Medallion architecture, Lakehouse architecture, stream processing, the internals of Spark, etc. Now, finally, I want to leave you with some architectures that are used in batch and stream processing using Spark or any other stream processing engine or batch processing engine for that matter. The first one that I wanted to discuss is the Lambda architecture. And it is an old architecture, but it is still relevant. Now, these architectures are used to implement certain type of use cases. It is not the case that you will be using Lambda architecture everywhere, wherever you are using Spark batch processing and Spark stream processing. This is just one of the architecture wherein you combine both of them. And if you choose to, you can use Lambda architecture. And whatever it says, whatever architecture it talks about, it is just a recommended one. It does not necessarily mean that you have to use the Lambda architecture just the way I discuss it here. You can have your own version of Lambda architecture also. And there can be different versions of Lambda architectures in different organizations. The architecture that I'm going to talk about is not the only one that is used in Lambda. First of all, what is this Lambda architecture? And you have to understand the Lambda architecture is not AWS Lambda or Python's Lambda function, etc. or the Lambda function that we have used in Kafka. This is a separate architecture altogether, which is used to describe data processing architecture. Now, this is a recommended architecture which combines batch and stream processing both. So if you have both batch processing and stream processing, you can use the Lambda architecture or any of its forms to implement your batch and stream processing layer. The way it works is like this. First, we have the batch data, and you already know what batch data is. I have talked about batch data in the Spark batch processing section. Then we have streaming data. You also know what streaming data is. But what happens is that the processing of these two data sources are very different. In batch processing, we use batch APIs. We use the data frame reader, data frame writer, etc. to read data and write data. But in case of stream processing, we use similar forms like read and write or data frame reader and writer, but we use read stream API and write stream API. Also, we have event processing, we have windowing, etc. These concepts are not there in batch processing. So the processing requirement for these two are very different. That's why when you use batch data and when you want to process batch data, you create a batch layer. Now, when I say batch layer, it is the entire data engineering layer that I have shown you already. You have the ingestion layer, the load layer or the storage layer. Then you have the processing layer and then you store it again. Just like we have batch layer, we have stream layer also, which is also called as speed layer in the Lambda architecture. Now, stream processing, again, you have the ingestion layer. It can be Kafka, or if you are using AWS native, you can use Kinesis. But in most of the cases, you'll be using Kafka because that is cloud agnostic. And AWS also provides a managed service for Kafka, which is AWS MSK. After you do the ingestion, you use Spark streaming to process the data and then you store the data somewhere, mostly using for each batch sync. And whenever you store or wherever you store, that is called the serving layer. And the serving layer would be common for both of them. So if you are using batch layer, it would store the data, let's say in data warehousing system or maybe in OLTP databases. Typically for batch processing, you store the data in data warehousing system. And if you are using streaming data, if you are using stream processing, you can store it both in OLTP or data warehousing or data lakehouse, depending on your use case. Whatever technology or tool you choose to use, that is irrelevant because all of them can be there in the serving layer. You can have OLTP database in the serving layer, you can have data warehousing system, you can have NoSQL database, you can have Lakehouse, and so on. So serving layer is the layer where you store the final data. After all the processing are done, you store the final data in the serving layer, and from there we have consumption layer. It can be downstream applications, it can be queries that are run using reporting tools like Power BI, Tableau, Click, etc. It can be downstream applications or APIs also, which get the data from serving layer. And these are called consumption layer, which you already know. There can be scenarios when you use or you send the data directly from speed layer to the consumption layer, which we have already seen in Spark stream processing. If you're using for each batch and you want to send that to an API, you can do that from the stream or speed layer itself. But if you want to run queries, obviously then in that case, you have to store it in a data stored in the serving layer. So this is what Lambda architecture is. And what it says, you process batch data and stream data separately, but you store the final data in a serving layer, which can be used to serve multiple downstream applications like queries, real-time applications, or any other reporting applications, etc. So the Lambda architecture tells you that you have to have a separate batch processing and stream processing. You cannot map them together, or you cannot process them together. And you might have to write the same logic multiple times. When I say multiple times, once for batch processing and once for stream processing. The batch processing might itself can have multiple logic. So can the stream processing. But what I'm trying to say here is that whatever logic you write, you have to write it for batch data also and stream data also separately. And eventually you'll have to converge them in the serving layer. That's what Lambda architecture says, that you have to have a separate batch processing and a separate stream processing. And because of this, it brings in pretty complex architecture, because if there are any changes for that matter, maybe in the batch layer or in the stream layer, you have to make sure that modification of one layer does not break the other layer. So there can be a lot of programs in the speed layer and there can be a lot of programs in the batch layer in your data engineering pipeline, which eventually writes to the serving layer to multiple databases. And let's say you are changing some of it in the batch layer, and you have to make sure that change does not break the speed layer, because you are eventually landing all the process data in the serving layer. Not only that, let's say you want to change something or some schema in the serving layer itself, and let's say that is a data warehouse, let's say Redshift or Snowflake, and you want to add some column, change some column, or you want to create a new table, or you want to have a new complete data mart setup. And you have to make sure that because of your setting up a new architecture in the serving layer, the batch layer and the stream layer should not get impacted. So that makes the entire architecture pretty complex. Now, as I said, whatever I'm showing is not the final architecture. Of course, you can have separate implementation of the Lambda architecture, but the essence of the Lambda architecture is that you have to keep the batch processing separate from the stream processing. Now, because of all these complexities and all these overhead, there came Kappa architecture, which simplifies the Lambda architecture further. And it is a very famous architecture. And the underlining of Kappa architecture is that everything is stream data. And you can use the same code for both batch and stream data. Now the question is, how can we consider everything as stream data? Because if you're using database or file or data warehouse as your source, or APIs for that matter, you might have to use batch processing. For database, data warehouse, and files, definitely you'll have to use batch processing. But for API, you can use either batch processing or stream processing. In any case, how can you consider the batch layer to be stream data? Now there comes multiple different tools and technologies. For example, for file data or for file sources, you can use Spark stream processing pattern, where files can be used to send streaming data using file trigger. I have already shown you what file trigger is. Similarly, for databases and data warehouses, you can capture all the modifications and send them to Kafka, and then you can use Spark stream processing to process that. What I mean by that, let's say we have both batch and streaming data. So we have this stream and speed layer. This layer remains the same, which is essentially the processing layer. The ingestion, storage, data processing, and final storage. Now the storage can be database, data warehouse, NoSQL database, Lakehouse architecture, Medallion architecture, etc. All of them come inside of this speed layer. And in case of Lambda architecture, all of them comes in the batch layer. So for streaming data, there is no concern, because you can ingest stream data just like sending it to Kafka. So you send the streaming data to Kafka, and then from there, you design your speed layer or stream layer. How do you do that for batch data? Now, as I told you, for batch processing layer, it can be database, data warehouse, or files. You can capture all the data mutations or data modifications, which is called CDC. Full form of CDC is change data capture, and its entire purpose is to capture all the modifications that are being done in databases and data warehouses. When I say databases, it can be relational databases or SQL databases and NoSQL databases also. There are tools available which can be plugged into the database engines, and those tools can capture all the data modifications from the source databases. For files, we do not have a separate CDC layer. We do not have a separate tool to capture the modifications, because for file, we have already seen file-based trigger. Now, from the CDC layer, you put it to the stream layer. And how we can do that? All the change data capture tools. Let's say on AWS, we have AWS DMS or Database Migration Service, which can be used to capture all the data changes from various source systems. And you can put DMS in the CDC layer, and the target can be any message broker like Kafka or Kinesis. So from DMS, you can send it to MSK or Kinesis, and by doing so, you are essentially sending the batch data to a speed layer. There are other open source tools also like Debezium, which can be used to capture the data changes from various different database sources, and all the changes can be streamed to Kafka or AWS MSK. And in doing so, you are converting the batch data processing to stream data. So that's where everything is stream data comes into play. Now, there might be a question, what about the data which are already there? Let's say you are starting or designing the Kappa architecture now. What about the existing data? How we can move the existing data to the final serving layer? We can do that using batch processing. You can do a one-time processing of the existing data, read it from various sources, make all modifications, apply all transformations and changes and aggregations, and then put it in the serving layer. And thereon, you can use CDC tools to capture all the data changes and put it to the stream or speed layer. And from there, you can insert it to the serving layer, and finally the query, consumption, and applications layer. So that's what Kappa architecture is. And the advantages of Kappa architecture is that we can use a single pipeline for both batch processing and stream processing. As you already know that batch processing is used for historical data changes. We can do the transformation and modification and send data to the serving layer. And stream processing is real-time data ingestion. The biggest advantage of Kappa architecture is that it is much simpler because we only have a single stream processing layer. But as I told you that if you have existing data and you are applying the Kappa architecture in between, let's say you are designing the Kappa architecture for an existing system. Now in that case, you have to load the data from different batch sources and then load it to the serving layer for one time. So that's what Kappa architecture is. Now, as I said, this is not an exhaustive architecture diagram for Kappa, but the essence again is that every data should be processed as if it were a stream data. So the implementation can vary, but the underlining is that you have to make sure that both batch data and stream data are processed using streaming pipeline. So that's what Kappa architecture is. Yes. So this concludes the entire Spark concepts section. Of course, there would be projects. I'll be giving you multiple projects in the next sections, but let's summarize what we have learned in this section. So we have talked about for each and for each batch sync. For each batch is way more famous than for each, because in for each batch, each micro batch is sent as a data frame to the function that you define. And the moment we get the data as data frame, we can apply all the data frame transformations that you have learned so far and store the data in file, in data warehousing system, NoSQL database, SQL database, or any other data store for that matter. Using for each sync, we cannot use data frame because the entire record is sent as a row to a Python function. And we'll have to apply Python custom logic to do the transformation and do the processing and then store it in various different data stores. Then we talked about stream to stream joins. There can be use cases wherein you might have to join multiple streams. So I have shown you that also, and there are certain considerations. For example, you'll have to make sure that watermark is available. Watermark should be there. At the same time, checkpoint location should be there. And in the join condition, you have to make sure that the event time is considered in the join predicate. Stream to batch processing is much simpler. However, I did not show you any hands-on, but in the fraud detection project, you'll have to apply stream to batch joins. Then at a high level, I talked about available now batch, which is a one-time trigger. Whatever data is available in the Kafka topic, those will be processed and the Spark streaming application would be terminated. That's what available now trigger is. Then we talked about an experimental streaming architecture, which is continuous processing. And in this case, the data is processed as soon as it is available in the topic and when the daemon gets the data and sends it to the Spark streaming application. There is no processing time trigger needed here. The trigger is continuous and we mention a certain duration after which the checkpointing would be saved or the state of the stream would be saved in the checkpoint location. Then we ended with two different architectures, which is Kappa and Lambda architecture. So that's all about Spark processing. Thank you so much for tuning in. I hope this entire course was helpful and informative for you. And I hope you start the journey towards your data engineering career. So please visit my website and look out for other contents also. I'll be uploading multiple volumes of machine learning, which I'll start after this is over. And before I sign off, just wanted to tell you that we have only one beautiful earth. Look at our earth, how beautiful it is. And this is not only for humans to live. This beautiful earth belongs to all the species that are there. So let's live and let live others also. Let's avoid using animal products apart from food, maybe like leather seeds, bone china, or any other animal products that are out there. Please avoid those. And if you avoid those, it would help the animals and a lot less animals would be killed. And thanks again. If you like my content or if you like my course content, please refer it to your colleagues and friends. And see you in the cohort in the live discussion. Thank you.